Okay, today we're talking about ensembles, or ensembles, ensemblize, ensembles. Today we're talking about ensembles, and this is going to be 3 lectures about ensembles. The first one is going to talk about bagging and random forests. The second one will be boosting, and the third one is another technique called stacking, but also more generally, how to combine models to achieve your machine learning engineering goals, not just your modeling goals. We'll be implementing as part of the assignment part 2 of this, the boosting part of it, but part 1 will just get you oriented on what ensembles are, introduce a few of the first algorithms, and head us on our way. So let's get started here. Now, remember in the last lecture we talked about bias variance challenges. Big problem, each model bumps into limits. Well, this is because simple models can't represent the complicated thing you're trying to do, and complicated models overreact to the variance in the noise and get messed up. Well, what if you could avoid those problems by taking simple models and turning them into a complex model, or taking complex models and having all the variations that they bump into cancel each other out? And that's exactly what ensembles is. Instead of learning a single model and using that for your prediction task, why don't you learn a whole bunch of models and combine them? If you combine high variance models, you can get rid of some of the variance problems through averaging. And if you combine high bias models, you can learn more power by focusing them on separate parts of the problem. And you'll often end up with a single ensemble that is easier to work with than any of the base models individually, and is also often a lot more accurate, like really a lot more accurate. And as I've said throughout the course, logistic regression, boosted trees, neural networks, those are 3 great tools to take with you as you start on your machine learning career. And now we're going to see what boosted trees are and how they can be a lot more accurate than logistic regression or just plain decision trees alone. So let's go through this a little bit conceptually. We'll give an example here, and then we'll start getting into some of the algorithms afterwards. Imagine you're trying to learn this concept. You have 2 variables, x1 and x2, and I guess this is predict 1, that's predict 0. That's the target concept that you're trying to get to. If you learn a decision tree, draw some sample according to that context, create a training set, validation, 2 parameters, blah, 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 you get a decision tree, and we all know that a decision tree cannot learn these non-axis aligned frontiers directly. It has to approximate it with a whole bunch of these axis aligned frontiers, so you get these jiggy-jag staircase thing approximation of the concept you're trying to learn. And in this particular case, I ran this thing and I had a 93% accuracy. It's not bad, but it's not great because it's a pretty simple concept. And the problem is the model doesn't match the concept well. If we add a lot more splits to this tree, it will maybe be able to have lower bias, but it might start to suffer from variance problems. And let's take a look at that. Here we go. I learned the same learning process on, 8 different training sets that were created randomly from the underlying concept. Each one was 200 samples, and the min to split was 5. And here's all the trees and their accuracies. And you can see that there's a lot of variance between these 8 trees in terms of how they represented this concept, how close they got to the concept. All of their accuracies, and these are all training set accuracies, are, whatever. Of course, if we put min to split lower and we up the number of samples, that'd learn the training set better and better and better, but that wouldn't get you around this variance problem that we're seeing here. What if instead of that, you took these 8 trees, learned 2 more friends for them, and then made a prediction by having all of them vote? And this is what I got in my little experiment when I tried that. And you can see these jaggy stairs are starting to round out a little bit as the votes sort of cancel each other out, and the decision frontier that this 10-tree ensemble is able to represent is getting closer and closer to that non-axis aligned linear separator. Of course, you could use more trees. There's 50. It's a little bit better, not a heck of a lot better, but maybe 50 is not enough. You can keep going, and now we're up to 500 trees, and the accuracy is starting to push up significantly higher than any of the base trees alone. And I didn't run the experiment out, but there's no reason you couldn't go to 5,000 trees or 50,000 trees or 500. Well, I mean, there's a reason, because you're going to run out of time. But conceptually, you could just keep adding more trees until you hit diminishing return, and you're like, well, what's the point of this? Why am I doing this? And now we'll go through the two main thought processes for ensembles in a little bit more detail. The first is to learn the concept many different ways and then combine them. And when you're doing this, you prefer to learn the concept with a base learner, that is the initial model you use. In the last example, it was decision trees, but you prefer a base learner that has higher variance. And what that means is that it's able to fit the concept. It doesn't necessarily have a high bias, but it learns the concept in many different ways, and it's sensitive to the noise, so its decision frontier bounces all around. And then when you combine them with voting, all that variance cancels each other out, and you end up with something that can have a lower bias with less variance. When you're doing this, the models are generically independent in that learning the second base model doesn't require knowing anything about the first base model that you learned. So you can learn them all in parallel. And as I said, it's generally robust to overfitting, because as you add more and more models, these variances tend to be random, and eventually they'll start to cancel each other out. Specific techniques that do this are bagging, random forest, and to some degree stacking. We're going to talk about lecture 1 today, lecture 3 somewhat. Now, the other approach to doing an ensemble, completely different mindset, different from what we showed on the last slide, is that you learn different parts of the concept with different models and then combine that. So you don't try to learn the whole concept with every model and then average to get rid of variance. You try to have each model pick a small part of the problem and just learn that part. And then another one just learns that part. And another one just learns that part. And to some degree, you're going to have some of this variance canceling from the first technique, but this approach adds another layer to that. And one nice thing when you take this approach is that you can have very high bias base models, also called weak learners, and I'm going to talk about that in a second, and high variance, and that this technique can cancel out both of those problems and give you just a completely better trade-off through a little layer of ensembling the models that you have. Now, to talk about weak learners, one of the first machine learning seminars, in grad school you have these seminars where you read a paper and you go and you present it to everyone else. I wasn't into machine learning. I was some software engineering, something, blah, blah, blah. I hadn't quite bumped into Pedro yet. In fact, this is the day I bumped into Pedro. So I go to that seminar and they say, hey, Jeff, next week present this paper. And they hand me this paper full of math. And it's all about weak learners and strong learners and blah, 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 and all sorts of, and it's basically the original boosting paper. And so the next week I'm presenting, and I didn't know anything about machine learning. I read the paper. I did my best. I got about halfway through, and Pedro, my future advisor, previous teacher of this course, gets up and says, let me take it from here. And he presented the rest of the seminars. That was my introduction to weak learners. Your introduction to weak learners is going to be hopefully less embarrassing and painful. A weak learner is any learner that can learn a concept better than just random. What this paper that I failed to present said, and what boosting is able to do, or this approach is able to do, is take any machine learning algorithm that's able to do even a little bit better than average and turn it through this ensemble technique into a machine learning algorithm that can learn a concept arbitrarily well. I mean, bumping into, other reasons that you're not able to learn the concept. And I think there's a technical mathematical definition of what that is. That is what this second type of algorithm can do. One important difference is that each model you learn depends on the previous model you learn, because conceptually the first model you learn is going to learn one piece of the problem. Then the next model you learn is going to want to learn a different piece of the problem. So you need to know what the first model did so you know where the second model should focus. And then the third model needs to know what those first two did, et cetera, et cetera, et cetera, so that they can eventually add up and learn all the parts of the problems appropriately. So that has some implications in terms of how you learn these models. And then another thing about these types of models is that they may overfit, where bagging and random forests tend to avoid variance problems by averaging. Boosting can, find little like noise in the error and have like 50 models go over and try to learn that exact piece of noise. So when you're doing boosting, you need to include overfitting avoidance techniques like we talked about, where you look at the train set loss versus the validation set loss and tune and use your intuition as you watch what's going on. Techniques here are boosting and GBM. A big one is called light GBM. Well, I won't write it, but light GBM is something that's used in practice as a way to learn boosted trees that's very effective in practice. But they're sort of, I'd say maybe over the last few years, a little bit of a renaissance in boosting algorithms that are being used broadly. And I'm hearing more and more boosting algorithms being invented. Like new ones are hitting my radar. New one just hit my radar last week. The point is that this is an exciting area that's getting a lot of attention because these techniques are quite effective. We're going to talk about boosting next lecture, maybe next lecture. For this lecture, we're going to talk about bagging and random forests. Let's go through bagging in a little more detail, and it's pretty similar to what I showed as that first conceptual kind of like layout, but I'm going to go through it again, and I'm going to describe more of the parts and more of the vocabulary. You start out in bagging with a single training set, and then you draw a bunch of samples from that original training set. So if you want to learn K trees, you draw K independent samples. We're going to get to exactly how to do that in a second, but conceptually, single training set, you would take your larger training set, split it into the train, validate, and test. Then you take the training part of your data set and draw these samples from it. Next thing you do is learn a tree on each sample, or whatever your base model is. It doesn't have to be trees, but it does have to be something that does not have a high bias for the concepts that you're going after. Generally, you would say that logistic regression wouldn't be a great choice to do with bagging. And in fact, when we get to random forest, we'll see that even decision trees in its vanilla form is not great, and that you can do extra tricks to add more variance to do even better with bagging. You've learned those, and then at the end, you do a vote to get the final model. So each model gets one vote. They each get to say, here's the classification that I'm going for. There you go. Or if you're going to do probability or regression, they each vote, and then you average the vote. They each get a uniform weight vote at what the output probability should be, and then you can apply your threshold here at the end. Here's pseudocode for that. Generate K training samples from the original training set. And the way you do it is you generate a Bootstrap sample. The next slide, I'm going to go through the details of this. So this is the type of thing I'm going to tell you multiple times because it's important. It's a widely used technique, and it may be a little bit counterintuitive right when you first hear it. So we're going to go through this a little bit. And if your original training set contains n samples, each of the K Bootstrap samples also contains n training samples. So each of these is the same size as this. And you'd be like, what? How can that be? I mean, you're taking a sample and it's the same size? Yes, well, you take a sample with replacement. And that means that the same instance, the same training sample from the original training set can be in one of these samples multiple times. So you could say that, we'll get there, but you could say this particular sample shows up in this Bootstrap sample 6 times. That's totally fine. I mean, it's unlikely to happen if you do the probabilities or whatever, but that can happen, and that's a way to add a little bit of interest to what each of these models are going to learn. Then, okay, you learn one model in each of the K, and then you combine their predictions by uniform voting. If you're doing probability, they can vote on the probability. If you're doing classification, they can vote on what the class is. A couple ways that you could do that combination. Here we go. This is called Bootstrap sampling. These are called, these training runs can be done totally in parallel because, this whole part doesn't depend at all on that part there. So that's a nice property of this. And then these decision trees that result are called the base models. So this is a bagging ensemble with decision tree base models. And each of these base models gets a uniform vote. And the final thing is called the ensembles prediction. Now, this does add a few hyperparameters to the learning process. One of them would be this K. how many things to learn there. Then you have to have the hyperparameters of the base models, which you still need to tune, and you may need to tune them dependent on K. It may actually matter. And then maybe there's some hyperparameters about how they vote or something along those lines. I don't know. Maybe. Everything we show in this class is the basic version of the algorithm. I don't want to confuse you with lots of options, but just to say, options are possible, as in everything with machine learning. Now let's go through Bootstrap Samples. Maybe this is belaboring the point, but I just want to show it to you again. So if this is your original training set, you have XY1, XY2, XY, so these are the different training samples. The way you take a Bootstrap sample from this is you take n, which is 5, and generate 5 random numbers between 1 and 5. And here's your array with the random numbers that you've generated. First is 3, 3, 2, 1, 5. Then you just move the associated sample over. So you could see here, this sample 3 appears in this Bootstrap sample 2 times, and you can see that sample 4 doesn't appear in the Bootstrap sample anywhere at all. Draw another Bootstrap sample by generating another 5 random numbers between 1 and 5. Maybe you'd want to be 0 based, I don't know. But you can see in this one you have sample 1 is in there twice and sample 3 doesn't appear at all. And that's the sample there. That's Bootstrap sampling. So you create your K Bootstrap samples, you run the base learners, you vote them. Pretty simple. That's the bagging algorithm. Couple properties of the Bootstrap sample. Most of them will contain duplicates from the original. It's pretty unlikely that you're going to generate random numbers that are like 1, 2, 3, 4, 5, some permutation of that. I mean, I guess you could calculate the probability of what would happen. I'll bet it's pretty low. Another thing you could calculate the probability of is how many of the original samples are missing in any particular Bootstrap sample. And that one I looked up, and 37%, on a 37% chance for each of these original samples to not end up in the Bootstrap sample. And Bootstrap sampling is a very widely used technique. As you do more machine learning, you'll probably see this name pop up again and again and again. So it's worth spending a little time on it, really sort of getting your head around it and what it causes, because it'll probably pay off in the long run. Now, again, to quickly summarize that bagging algorithm that we discussed, each model learns the concept a different way. The Bootstrap, as you're pulling those Bootstrap samples, it accentuates the variance between the individual models because they each learn on a different part of the training set. Now, if you had a model that didn't have a high variance and you didn't inject extra variance and they all learned the model like with the same stair step and you averaged it out, you'd end up with the same stair step, right? It'd end up looking exactly the same. And so you need base learners and Bootstrap sampling and other techniques to make sure that you learn the model in many very different ways. And then the voting tends to cancel out that variance without increasing the bias. That's bagging, simple thing to do. The next step along this path is random forests. And random forests is bagging with 1 or 2 little additional techniques. And for a while, like around the time I was working on the Xbox One and maybe a year or 2 before it, random forests were the thing. Everybody was using random forests. It was hot. Not anymore. You don't really hear, people don't really do random forests anymore. Except, I mean, it was even to the point where the first 2 times I taught this course, we implemented random forests. And I started in the lectures to say, well, random forest, blah, 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 everybody does boosting now. And a student raised their hand and said, well, if everybody's doing boosting, why are you making us implement random forests? Why would we do this? So this year I changed the assignment to boosting. And I'll admit, when you see it, boosting's a little harder to implement than this. So you may or may not want to figure out who that student was and thank them, or thank me, or give me some more advice on how to torture next year's students even a little bit better. But that said, let's go through random forests. Random forest, just like bagging, you build n trees, you build them on Bootstrap samples, so you're doing bagging, and here's the additional thing that you do. Each tree that you learn, you restrict the features it can use to add additional variance at the cost of bias. And this just accentuates how the bagging approach can really deal with variance to the point where an already high variance model, decision trees, it's not enough variance. You can add even more variance, and that tends to result in models that generalize much better and give you much better bias variance trade-offs. And then at the end, you combine by uniform voting, just like we said before. Here's an example of what it looks like to grow a random forest. So you learn a model, you grow a random forest. Now we're talking. If this is the training data and X has 3 features, so you have feature X1, X2, X3, the first tree, you take your Bootstrap sample, like we talked about by, randomly, blah, 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 and you also randomly select several of the features to use. And that means that this tree may not use X3 in any of its splits, just completely off the table. Grow the tree using the regular decision tree learning algorithm that you guys probably have implemented by now, or it's in your homework and you should start implementing it soon. Start pretty soon, don't fall behind. You might learn a tree that looks like this. You see it tests on X1, it tests on X2, there's no X3, that's off the table. Then you want to grow another tree, so you do a whole bunch of more random numbers, and you do another Bootstrap sample, and again you select features, and now you have different features. Maybe one of these features is really good. Let's say X3 is the best feature that you developed, and any tree that uses X3 is going to select it first and is going to learn the concept along a pretty similar contour because X3 contains a lot of information. Well, in order to get more variance, you want to tell some of the models, hey, that good feature, which all your friends are depending on, try to learn the model another way. And that will encourage the trees that cannot use the good feature to have possibly more structure because it needs to glom together a lot more weaker pieces of evidence to make its decision. And that's the sense in which restricting features can do a really nice job at adding variance, forcing the trees to understand the concepts in very different ways. Here is just to prove that I could do it twice. Me drawing this tree wasn't a fluke. I've drawn another tree. So now, right? You can count on me for the trees. I'll even let you see the whole thing. And again, X1, X3, no X2. That's the training side of it. Now for the prediction side, I'll just walk through the example quickly. Here's 4 more trees, even more evidence of my tree success. So this is a random forest with 4 trees that learn the concept 4 different ways. Now, if you want to classify this sample, what you do is take that and pass it through each of the trees. So X1 equals 1 is false, so Y equals 1 for this tree. For this tree, X2 equals 1 is false, so Y equals 0 on that tree. For this tree, X3 equals 1 is false, X1 equals 1 is false, so Y equals 1 for that tree. And for this tree, X3 equals 1 is false, so Y equals 1 there. And the majority vote, so your Y hat would be, for this tree would be 1, or you might say your Y hat is like 0.75 and then use a threshold across the votes for the trees. Or you might let each of these leaves contain the distribution. Instead of voting 0, that tree might vote 0.15 or something like that. And then you just kind of like sum up the weighted votes to get the overall vote. All those things are options. I'm going to leave this up and it's Jeopardy time. Fill in, stare at this slide a little bit, do a few more of those. Okay, that's, pause it. I don't need to sit here for all day. Just pause it if you want to go through some more examples, but it's pretty straightforward. Here it is in pseudocode, and maybe I belabored this slightly because last year everyone had to implement it. But you'd say an array of trees, so that's where your random forest is going to build up. For I in the number of trees that you're building, you take a Bootstrap sample from the original training data. Now remember, you have the validation and test data off to the side. So you use just the samples reserved for training, and then you have, for this tree that I'm building, there's the Bootstrap sample that I'm going to learn. Then you also do randomly select feature IDs. And maybe there should be maybe it should be xtrain 0. That could be a bug there. So you take the number of features in the first training sample, and you'd say, from those, select me, let's say 7 indexes. Now the way to set number to use, this could be a hyperparameter. In the original paper, it was something like the square root of the number of features, but it depends a lot on the types of features you have. As I mentioned before, if there are some very strong features, you may get the case where you learn 10 trees that have the very strong feature and do decently, and then you learn 90 trees that are basically garbage and learn nothing. So you have to be careful when you restrict the features that you use, that you generically leave enough information in the remaining features so that you're able to learn something, right? And this could be a problem if you're using many features. In the SMS spam example, you got like 10,000 most common features, but it turns out only like 15 of them are really valuable and the rest are just like crazy gibberish words that don't occur too much. You'd have to be careful about how you set this number to use, or you could get in trouble. You append your next random forest by growing a tree on the Bootstrap sample with the features to use. And in my mind, this is a bit mask, something along those lines that you can just pass along. Then when you've learned all the trees, you would do a classification by predicting by majority vote among the trees on the test set if you want to, or you could do a probability estimate by counting the votes of the trees on the training example and dividing it by the number of votes that you have across the board. And then, of course, as I mentioned several times, this process is totally independent. So you could change this for loop here into one of those parallel fors using joblib and get a very nice acceleration across your CPUs. So you could learn one tree per CPU or something along those lines and get some parallelism out. There you go. That is Ensembles Lecture 1. 1/3 done with that. Breaking it up to give this some time to stew so you can think about it a little bit. Here's the quick summary. Ensembles combine multiple base models to make a single prediction. Ensembles help with the bias variance trade-off by either number one, taking base models that tend to have high variance and injecting even a little more variance and then averaging it out, or taking weak learners that tend to have high bias and focusing them on different parts of the problem so you can stitch together a bunch of weak learners into a stronger learner. We'll see that in the next Ensembles lecture. Bagging is good to use when the base models have low bias, high variance. And what else did I say here? Random forest with bagging, use feature restrictions to encourage additional variance. And for a period of 2 or 3 years, among many types of problems, particularly computer vision, random forests were a really awesome approach to use. No longer. All right, thanks everyone. I'll see you next time.